real exam questions. This is question 61. It's about column design in general. Sketch in a graph the relationship between the bending moment m and the curvature 1 over rho. When it is independent of the reinforcement and the stresses inside the cross-section of the column, it's the external stability. And make also the graph when it is dependent on the reinforcement and the stresses. So that's the internal stability. Now draw both graphs on one figure or on one graph. In which area or points is there equilibrium between the external and the internal forces? Prove the relationship between the bending moment m and the curvature 1 over rho with external stability only. We start with the external stability independently from reinforcement and stresses. So we have the diagram on the y-axis, the bending moment, on the x-axis, the curvature. And for a certain value of a normal force, we get this relationship, where the slope of the curve, the tangents of this angle, is equal to NED times L0 over pi squared. And the element, the distance from the point 0 and where the curve is cutting the y-axis, this is the value m1. So let's prove this. Total bending moment is the bending moment of the first order plus the bending moment of the second order. The bending moment of the second order is the applied load times the eccentricity of the second order. The eccentricity of the second order is L0 squared times the curvature and divided by 10. Pi squared is almost 10. This we still have to prove because we use it in the proof of this red line. So we still have to show why this is the case. It will come just now. And then you can substitute, and this is, if you look at this carefully, this is a linear or the equation of one line with m1, which is this space, and the slope is there. This is on the x-axis. So if you can prove that E2 is equal to that, then we have shown what the relationship is between the bending moment and the curvature for external stability. This is the column under consideration, loaded by a normal force and a bending moment with a deflection E2. We have chosen this coordination axis. The total length L0 is this. And the deflection here is negative because we start here with y is 0. Total length of the column is L. We look at the elastic line. Y, the elastic line is y in function of this of those coordinates is minus c sinus ax, with c and a not known yet because the deflection in our system is negative. That's why this minus c. This is valid for x be L0 over 2 up till L0. This is L0. So from there to there, that's real. This is not realistic. So we take this portion. Boundary conditions to find C and A. First, we start with this point. Obviously, when x and y is 0, then this equation is okay. Then we take the second point on top. That is when x is L0. X is from there to there L0, and y is 0 because we are just on this axis. Then we fill it in this equation, and we see that 0 must be equal to minus C sinus A L0. Of course, C equals 0 is a solution, but then we end up with nothing. So we suppose that 0 is not 0. So the sinus of this must be 0. And that means that A must be pi over L0. And point 3 is where y is minus E2. And this is E2. This is negative. It's minus E2. And x is, of course, from there to there, L0 over 2. We substitute it in the equation, and we find that C must be equal to E2 because this is the sinus of 90 degrees. So now we have, because of those conditions, we have now A and C, and the elastic line is given by y is equal to minus E2 sinus P over or pi over L0 times x. Now we know that the curvature is equal or almost equal to the second derivative. And we have the equation of the elastic line, the function y in function of x. So let's apply this. We take the first derivative. Then we have, of course, minus E2, and the derivative of sinus is cosinus, times the derivative of this, which is P over L0. Then we take the second derivative. So it is again this, but the derivative of cosinus is minus sinus, and again the derivative of this. So we end up with this equation. The second derivative is equal to the curvature. So we have this now. And when x is equal to L0 over 2, that is at the base of the column, we see that if you fill x equal L0 over 2, you will see that the curvature is equal to E2 times pi over L0 squared, or we just mentioned it in E2. So this is the value that we used in the previous slide. So this is proven by this elastic line. Now we will look at internal stability dependent of the reinforcement and the stresses. We have the bending moment M and the curvature, but we know that the curvature is always the strain divided by the effective depth. So for a certain value of the normal force, we can make that relationship, something like that. We know that so the bending moment is a function of the strain in the steel and the strain in the concrete, certain function, depending on in which domain you are. But this function is well defined. And the normal force is also a function of the strength, but we've put it in a constant. We said this is NED. So now what we can do is for each N equals NED, we can now say look for epsilon S, construct this function, that the strain in the steel, you take a small value, for instance, it doesn't matter, 0.1 promille or something like that. Take for your first point, you take a certain value, you calculate the corresponding concrete strain in function of NED and epsilon S1 chosen, and you find epsilon C1, the strain in the concrete for the first iteration. Then you can calculate the curvature as a first iteration. It's 1 over rho. And when you got the curvature, you can calculate the bending moment. So now we have the curvature here for a certain value of epsilon c, and we have a certain point m, because m, this function is known, and we know what epsilon s and epsilon c is. So that is the first point of m1. So you start here and you have created 1 point. And now you continue with different values of epsilon s, and you do the same calculation and you arrive at this curvature. Now, when we put the two graphs together, the bending moment in function of the curvature, we have the green line, which is internal forces, and the red one, which is the external forces. Now we have 2 points where there can be an equilibrium. Let's look at the first at the point here. Then you will see, if you make this larger, that for a small increase of the curvature, the external forces are growing faster than the internal forces. So it means that the difference is negative. So it means that you do not have a stable condition. On the other hand, on this point, the growth with a small increase of the curvature gives you a difference which is positive. So the internal forces rises faster than that of the external forces. So that means that you have resistance. That means you have a stable condition because it will always go back to this point. So an equilibrium is stable when with a small increase, delta, in curvature, the eccentricity of the internal forces rises faster than that of the external forces.